So last week we left off talking about temperature and changing the concentrations of your products or reactants and Le Chatelier's principle and what a reaction would do if we changed those things. And one of the things that we talked about was just kind of thinking in terms of K, that K is going to be let's take this reaction here, our products over our reactants in the same phase. So NH3 squared divided by N2 and hydrogen gas cubed. And we said that Q equals the same thing, but Q can be at any time in the reaction. There we go. I was talking and not writing. Q can be at any time in the reaction, and then we discussed what the value of Q can mean for a reaction itself. So we said, so if Q equals K, we're in equilibrium. If Q is less than K, we haven't gotten to equilibrium yet, so the reaction is going to go towards the right. If Q is greater than K, well, what does that mean? That means that I have more product than I have reactant, so my reaction is going to shift to the left. And we use that in talking about the change of concentrations and where heat's going to go. Well, now I want to look at what happens if I change pressure. So going back to this reaction that we've been using, if I increase the pressure of this system, what do you think is going to happen? Am I going to shift my equilibrium to the right, to the left? What do you think? Pause for a second and think about it. Okay, so now let's think about what happens when I change pressure. Do you think I'd increase or decrease my volume? So hopefully you're thinking in terms of decrease. And one of the ways you can look at that is with a piston. If I decrease my pressure, I decrease my volume, I have more collisions going on within that smaller volume, which increases the pressure. Now, as far as my equilibrium goes, let's go back to your question, or to the original question. I've shrunk my volume, which has increased the pressure. Is that shifting my equilibrium to the left, to the right? Is it not having any impact at all, or can you not tell? So let's think about this. If I have 2 moles of gas, 2 gas moles here, and 3/4 moles here, how can equilibrium shift to counteract the impact of the change in pressure? Well, if I have fewer moles of gas, I have fewer collisions. That decreases my pressure. So what equilibrium is going to do then for this one is it is going to shift it towards the right. Now what happens if I decrease my pressure? Pause for a second. Okay. The exact opposite is going to happen. I've decreased the pressure. That means I'm going to create more moles of gas to balance out to achieve the same pressure that I had in that initial reaction. So it's going to shift it to the left. And I love when I catch myself off guard about it. The next picture that's going to come. I should have put this up on the screen while we were talking about it. Shows the decrease of pressure, so the increase of volume. So you can see that everything has more space to move around. So to come back to the pressure that it was at when it reached equilibrium, we're going to see the shift where we're going to have an increased number of gas molecules. So let's look at our octane reaction again, and just to remind you that this is the octane. In this one, I have how many gas molecules of gas on the left and how many molecules of gas on the right. And do you think that I would get more or less of my octane if I increased the pressure? So pause and think about that. So let's see. I said in the beginning, I'm like, okay, we have 1 mole of gas here, 8 moles of gas here. Everybody's in the same phase. So on this side, I have 10 moles. On this side, holy moly, I have 17. I have 25 moles. So if the pressure increases, I've made the volume smaller, So I want to decrease the amount of gas molecules. So I'm actually going to produce more of my octane. So the moral of the story there is if I increase the pressure, the shift is going to be towards the side with the fewer moles of gas. Sorry, got to get my train of thought in line. Okay, 3 equations I want you to think about. The first one is carbon dioxide to carbon monoxide. Second one is hydrogen and iodine. And the third is ammonia and H2S. And we want to know if the pressure in each system is reduced, which way does equilibrium shift? So pause for a second and think it through and then come on back. Okay, so the key here is that I am reducing the pressure, right? So let's say I have 2 moles of gas on this side and 3 moles on this side. So if I reduce the pressure, that means the volume is getting bigger, then I'm going to produce more gas molecules. I can take up more space and then increase the pressure to where it was before. Hydrogen and iodine, let's see, we have 2 moles here and 2 moles here. Oh, same amount of moles. So if there's the same amount of moles, nothing happens. Everything stays the same. All right, now this one. So I have 2 moles on this side and 1 mole on this side. So that tells me if I reduce the pressure, I'm actually forcing the reaction to go back that way to counteract, to produce more moles. So if my goal is to produce more product, then what would I want to do here? Would I want to decrease or increase pressure? Yeah, I would increase the pressure, forcing the reaction to generate fewer moles of gas, which makes the reaction favor the product. So it's pretty cool. So now let's go back through this before I move on to catalyst. Increasing pressure, the reaction is going to go in the direction of fewer moles of gas. Decreasing the pressure of the system, my reaction is going to go in the direction of whichever way produces more moles of gas. If I have equal amount of moles on both sides, nothing is going to happen by changing the pressure. So let's talk about catalyst. Back in 162, we define catalyst for you. And what we said is that it's something that helps speed up reaction and it's not consumed during the reaction. So the hint there is that it is speeding it up, but it's not producing more. It's just making it more efficient. And one of the ways that we can think about that is like in terms of our activation energy, where we have, before catalyst is applied, that's our activation energy from here to here. And if I want to add in a catalyst to speed it up, all I'm doing is decreasing the activation energy. So I end up with something like maybe that goes like this. So the nice thing about this is the activation energy is decreased in both directions, but I haven't made more. I'm still only going to make as much as I could make without a catalyst. It just goes faster. So some of the things to keep in mind when you're looking at a catalyst, it does not get incorporated into our equilibrium constants. And I mentioned this in, I think, the first lecture. In part for that is because it's going to exist on both sides of the reaction. So if you think in terms of your equilibrium constant, it's going to get canceled out. It's going to live on the top and the bottom of the reaction. So it doesn't live there. So let's bring all of what we've talked to together. I am going to, there should be a list of things here. There we go. Give you a list of six things to consider with this reaction. I think one that we've done already. I think we did it in reverse with carbon monoxide and hydrogen. No, we did do it with pencil lead. And we talked about pencil lead and turning into hydrogen gas and making it combustible gas while you're writing, which would be a bad thing. And we talked about the temperature. So here's that reaction again. So we're going to have carbon and water going to carbon monoxide and hydrogen. And we want to know what is going to happen under these certain circumstances. So we have our delta H. Remember, it's positive, so is that endothermic or exothermic? So it's endothermic. First thing I want you to do is to write out an equilibrium expression for this reaction. I'm going to start by writing that myself when you come back. And then I want you to think about what's going to happen when I add more water, when I transfer it to a larger vessel, when more carbon monoxide is added, when the temperature is increased, or a small amount of carbon is removed, or a catalyst is added. So your choices are the A, B, C, D. Go through and decide what's going to happen and then come back. Okay, so let's start with looking at what our equilibrium expression looks like. So my Kc is going to be my carbon monoxide gas and my H2 divided by just my water. Remember, why didn't I include carbon? It's not in the same phase as everybody else. My water, my hydrogen, and my carbon monoxide are. So they all go into the equilibrium expression, but not the carbon itself. So what's going to happen? In terms of my Q, remember that has the same expression. So Q is going to equal the same darn thing. CO, H2, divided by water. So if I add water, my Q is going to decrease in size, decrease in size, bigger denominator, overall smaller number. So that means that my equilibrium is going to go to the right. And that means I'm producing more H2. If the mixture is transferred to a larger volume, well, what's happening there? I am, a larger volume, I'm decreasing the pressure. Okay, that's the first thing to look for, and then ask yourself, how many moles of gas do I have? I have 1 mole of gas on this side. I have 2 moles of gas on this side. If I have decreased the pressure, then I'm going to favor the side with more gas molecules. So my equilibrium is going to go to the right. More carbon monoxide is added. So what's happening here? What's happening to my Q? Come over here and I look at this. More carbon monoxide is added. My Q has increased. The value of carbon monoxide is in the numerator. So I've increased Q. Q is greater than K. That means my equilibrium is going to favor my reactants. If the temperature increases, okay, so we have the delta H is positive. That means this is an endothermic reaction, and one of the things that I said is that we can think about that then as adding heat here. So heat plus, it is on my reactant side, products over reactants, so it'd be like down here if you want to think about it that way. So what impact would that have on Q? Well, again, that would be decreasing. So Q would be decreasing, and that means my equilibrium would go to the right because it wants to get bigger in order to, so I need to make more of my carbon monoxide and hydrogen in order to get to K. Now, removing a small amount of carbon, what's going to happen here? Well, carbon's a solid, and it doesn't exist in either of my expressions for K or C or Q. Nothing happens. Nothing. It's not going to have any impact on my equilibrium. What about adding the catalyst? Yep, again, nothing. So adding the catalyst gets me to equilibrium faster, but it doesn't increase the amount of product or reactant that I have. So again, looking at like our reaction pathways that we'd have, where we'd be like, so I start off with no product, and I get here, and here's my reactant going like that. And we said that this stage right here, this is our kinetic area, and this is our equilibrium, when everything stays the same. Okay, so adding a catalyst is just going to make this a steeper slope, be like something like this instead, and leveling off, evening off, kind of the same, leveling off. So just shifts how quick we get to equilibrium, but doesn't have any impact. And that's it. So the rest of your homework questions for chapter 14 are very similar to what we've covered here. Feel free to ask me any questions. Some of the Discord, don't forget, you can go there and ask me questions as well as on Canvas. And I will see you soon.